So thanks everybody for coming and joining us on this very exciting event. I want to remind you that we're actually recording the session today. And before we begin to talk about the facility itself, I want to introduce Dr. James Fitzpatrick, which is the ANFF Chief Operating Officer. And we'll say a few words on how this facility fits into the national infrastructure landscape. Welcome, James, and thank you so much for coming.
Thank you, Sergio. I'm absolutely delighted to be here. We first heard about this Fibre Bragg grating facility probably 18 months ago, and we're really excited about the fact that it's now part of the ANFF National Research Infrastructure, and that we're able to provide its expertise and its capabilities to the broader landscape of researchers and industry across Australia. So for those of you who are not aware of what the Australian National Fabrication Facility is, we are a nationally funded organisation who provides access to expertise and instrumentation that provide fabrication capabilities across the country. We are open access, and we really do open our doors to whoever needs our facilities. And we do try and provide them with the expertise to ensure that whatever fabrication project they have, they can get a successful outcome in the shortest possible time. So with that, the idea of the Fibre Bragg grating facility, when it came across our desks, really did fit beautifully inside of that. The advanced Fibre Bragg grating facility that is at University of Sydney now is world leading. It's a great sovereign capability to have here in Australia, and it provides us with the ability to do things here in Australia that we might not be able to do anywhere in the world. But certainly we're able to do them on our doorstep and push those research projects and those industrial projects and products that come from those into these realms that we wouldn't be able to do otherwise. So with that, I am fully supportive of this facility. I think it's a wonderful addition to the national research infrastructure landscape. And I'm really excited to hear about some of the projects that are already running through its hands. And hopefully this webinar will allow others to join in and access those capabilities for the benefits of their projects. So thank you very much, Sergio, and over to you.
Thank you very much, James. We're indeed very excited about this opportunity and the support from ANFF. So we're actually looking forward to get this facility at full capacity. So I'm just going to start. I've been asked to give a brief intro about fibre gratings and applications, and also to explain a little bit of how this facility is actually a very particular facility in a sense in which it got the capabilities that many other facilities around the world don't have. So I'm going to start with a bit of history here, and I'm guessing that many of you online at the moment have been during that time part of this history itself. And it's back circa around 1999 when it was what is called Australian Cooperative Research Centre. And it was at the time the largest CRC centre in Australia. So just to give you an idea, during that time, it was a lot of investment. It was also at the peak of the telecom before the fall, unfortunately, but it was at the peak of the telecom time, and then at the time was a lot of a big ecosystem on the different companies, initiatives, startups, etc. At that time in 1999, once what the Redfern Optical Components ROC was actually created, and during the next 5 to 6 years, it received around $20 million investment. And the focus of that particular company, ROC, was in fibre grating products, right? And basically for the field of optical communications. So during all that time, it was actually was one of the only companies who actually managed to push forward and to grow and grow. And then as it happened in 2010, T-Sudcom, the connectivity then, which is one of the major cable companies, and in particular submarine cable companies in the world, acquired ROC. And then from there until 2018, when T-Sudcom became Sudcom, this actually facility further developed fibre grating technologies in the writing domain, and also in the packaging and product, etc., etc. So as it happens, in March 2020, Sudcom decided to close foreign business, basically, and the Sydney factory was one of them. And we saw an opportunity there, and we managed, as Jen described, to bring ANFF on board. So we're extremely happy for this, and that all this became a reality. And we moved all the facilities down to the University of Sydney, and we started installation and commissioning in early 2021. Okay. Now, let me give you a basic principle of what a fiber Bragg grating is, and basically the most widely used technology is to get to create an interferogram with UV laser light and to project that into the core of the fiber. When you do that, you can't, due to the photosensitivity of the fiber, you create a periodic or index modulation of the core, and this index modulation is reflected by the light propagating around that core. We'll see that that modulation, and it will have a response in the wavelength, which is defined by the Bragg condition. This is the basic of a fiber Bragg grating, and I'll go further than that. And one of the things about fiber Bragg grating technology is a very mature technology, and it has many advantages over many other technologies. It has been used for long transmission distance. Is used because it got a perfect electric isolation, signal integrity, the size of those devices, and another important but not a small thing is the ability to multiplex and to be able to bring multifunctionality into the fiber Bragg grating. So as you can see here, what you can create is sensing technologies that actually can multiplex and can have different functions along the same piece of fiber in a very compact size and manner. So this is why the advantages of fiber Bragg grating technologies are. And just to give you a little bit of how they are used nowadays, it's a very mature technology in sensing and monitoring, and due to the multiplexing and multifunctionality. So one of the areas in which this is actually happened, there are several ones, is what is called process monitoring. In this one in particular, you can find these technologies in places like paper manufacturing, steel casting of composite structures, and even into oil exploitation. Then another area which is very big in fiber Bragg grating technology and sensing is structural health monitoring. And in this, you can have an active alert possible failures in the structures, and you can put that in pipes, wind turbines, bridges, and many, many more. Last but not least, have been recently used heavily in healthcare, in which you can actually use those devices with unique properties to enhance diagnosis, or even to actually aid on surgeries themselves. So this is actually quite exciting to see that this, in principle, basic technology got so many uses and important ones. Now, let me tell you a little bit to steer against towards why this capability is actually important and special. The standard way in which you write UV fiber Bragg gratings is, as I said before, is actually by creating an interferogram and projecting that into the core. The most widely used one is what is called direct phase mask. So you have a phase mask called a grating pattern that creates an interferometer, and that interferogram is projected into the core. So this is actually very easy to mass manufacture. It's the most used system in industry, and it creates simple gratings around the wavelength that is the mask is designed for. Another system that is widely used is what is called the Talbot interferometer. In this case, you have more flexibility in what wavelength you can actually target with this system. It's more sophisticated when you can create slightly more complex grating designs, and is mostly used in research and in some niche industries like fiber drawing, fiber grating generation, etc. So, but they still got limitations in what type of grating designs you can achieve. Now, let me go back to why this facility and why we are excited about this facility. Why this facility is important. This facility is based in what we call a Sanjat interferometer, in which actually have also acoustic optic modulators to tailor to actually mold the light, the interferogram that you can create. And in a very easy and passive way, you can design the response on the fiber Bragg grating itself for many different structures. So this is actually a technology that is Australian sovereign capability. It was developed over more than 18 years here in Australia, And in fact, we actually work out the numbers, and that is probably around 30 PhD students that work on this technology over the years. And it could be more than 70 hours, 75 years in senior photonics and mechanical engineers put on this system. So the ability to mold that interferogram to change on demand very rapidly and very effectively, that pattern creates the capability to do complex fiber Bragg gratings and to create devices that are very difficult to achieve, like DFB lasers with extremely line width. And also another one that we are very happy that we can actually retain here, which is the ability to create aperiodic fiber gratings that you will see later on in Joe's talk, for example. So just to give you an example, with that capability, what we can create is very complex designs here, in which we can change the intensity modulation, the amplitude modulation of that refractive index in the core at will in a very complex manner, and also the phase, which is the period that you see on the response of the grating. As an example, we got this device here, which to our knowledge is probably the first time that was Morse code was actually encoded in a fiber Bragg grating, and we have the audacity of spelled ANFF for this, and this is actually what this fiber Bragg grating is the response of this design in index modulation and phase of the grating. So now, last, what I want to actually mention, I want to actually introduce you the team. This is actually the heart and the soul of the facility. It's Dr. Ligo Luo and Dr. Goran Edbel, and between both of them got more than 40 years experience in R&D in photonics and fiber Bragg grating development. So we're actually very happy that we can retain the expertise and the know-how, and we brought them to the university supported by ANFF. So, and last, what I want to say, the rationale that we have for this facility, we saw an immense opportunity, as Jen described, in using this platform, not only to help researchers, but also to engage with industry and to retain a sovereign capability that have been many years, and was a very important thing within the Australian photonics community. So I think that with that, I have finished my presentation, and I would like probably to move on, and because my presentation was the introduction to the next speaker. So it's Dr. Scott Foster for the DSTG group, and he's going to be telling us today about DFB lasers in fiber Bragg gratings. How are they using sonar technology, and why we have been working with them in this capability with this fabrication facility. Thank you, Scott.
Thanks, Sergio. I think I can't share my screen. I think you need to unshare. There we go. Share sound. Okay, so that image that you can see on the right-hand side is a experimental fiber optic sonar system just settling on the floor of the Gulf St. Vincent in South Australia. So sonar systems are basically arrays of underwater microphones. We call them hydrophones. And this technology, this is the principal sensor technology that underpins virtually all undersea warfare systems. So this particular sonar is an ultra lightweight fiber optic seabed array that we developed as a benchmark system for our fiber laser sensor technology. So if you see that yellow cable at the in the foreground, that's part of the 4 kilometers of lead-in cable, which delivers all power all telemetry to all 8 sensors in this array via a single optical fiber. Those silver blobs in the center are some of the sensor housings. Inside each of one of them is a fiber laser hydrophone, which is really what I'm going to be focusing on today. The novelty of this technology is that by eliminating all electronic instrumentation and all electrical cabling from the ocean environment, you can achieve a sensor platform which is extraordinarily lightweight and hopefully very robust compared to conventional piezoelectric technology. So if you cracked open one of those sensor housings, what you'd find inside is that the hydrophones basically consist of a flexible mechanical beam, along one edge of which is bonded a distributed feedback fiber laser. So the fiber lasers, which are really the heart of the sensor, were fabricated at the state-of-the-art, really world-leading fiber Bragg grating facilities that have now recently been rehoused at ANFF Sydney, and that we're launching today. In fact, fabricated by Gore and LIGO. So the idea is that when acoustic pressure deforms the beam, That strains the fiber laser, which is bonded to the beam, which changes its frequency. And with the magic of interferometry, we can decode the modulation of the laser frequency. And this is what we end up with. Hopefully you'll be able to hear it.
Hello, my name is Jonathan Hedger. I'm an APR intern currently working in the Undersea Sensor Science Lab. And today is the 17th of December 2020. And we've made this recording to demonstrate passive interrogation of a fibre laser hydrophone at the end of 100 kilometres of single mode optical fibre.
Okay, in order to understand what's going on, I thought it'd be fun to go right back to basics. So basically, pretty much every optical fibre strain sensor can be understood in terms of interrogation of an optical cavity. So remember, an optical cavity is basically a reflective structure which traps light in a confined region. And when the optical wavelength is an exact harmonic of that physical cavity, you get a resonance. And when the length of the cavity changes, the resonance wavelength changes, or the resonance frequency changes, and that establishes effectively an equivalence between frequency, which you can measure, and mechanical length, which enables extremely precise measurements of mechanical deformation. So what I've tried to draw here is sort of a simple sensor system, which basically consists of a tunable laser, which is basically being tuned across the resonance of a cavity formed by two mirrors. And what you get is this characteristic transmission curve with a peak at the resonance wavelength. And obviously that resonance wavelength is going to shift as the cavity is strained. So if you thinking of it in really naively, you can essentially equate the resolution of the sensor to the width of that resonance. And the width of the resonance turns out to be basically determined effectively equal to the inverse of the cavity Q. So what that means is a higher Q cavity that you have, the more sensitive to strain your sensor is. It turns out that you can make extremely high Q cavities in optical fiber. So essentially instead of just writing a single grating, if you imagine writing two gratings and then bringing them together with a very, very precise phase relationship between them, and if you get that phase relationship just right, you can get a very, very high Q resonance. And the device that I've shown on the right-hand side there is the actual resonance structure of a device fabricated by Gore and LIGO for one of our sensors. So what you'll see is that broad grating reflection band, which is showing up as a transmission of extinction of almost 70 dB. So these are very strong gratings. And right in the middle is a very narrow feature. And that narrow feature in the center, that's our cavity. And it's extraordinarily narrow. In fact, based on the width of that resonance, we can infer a cavity Q of about 8 by 10 to the 8, which is comparable to the highest finesse cavities of any photonic device, and it's all in optical fiber. So it's beautiful technology. And that translates to a strain resolution of about 1 part in 10 to the 9, or nanostrain, which is quite good. But this type of passive interrogation of very narrow resonance features like this is not very practical. So now I want to talk about lasers. So there are a number of ways in which you can actually beat that naive sort of strain resolution limit. And one way is to activate the cavity. So we activate the cavity by doping the fiber with erbium ions. And when you pump those erbium ions, you basically turn the cavity into a laser, and the laser wavelength is exactly locked to the cavity resonance at all times. And so basically just by measuring the laser wavelength or the laser frequency, you can sense the length of the cavity in real time. And it turns out that the line width of these lasers is only a few kilohertz, and that corresponds to an equivalent strain resolution of the order of 10 to the minus 11. So we've actually somehow managed to pick up about 2 orders of magnitude of gain compared to that naive strain sensor. But it's actually even more to it than that. So the key to understanding these devices is to understand that at each instant in time, they literally produce a single frequency. And that frequency, you can represent that frequency as a wiggly line, which is wiggling around it, which is fluctuating in time. And the envelope of those wiggles, basically is your laser line width, which is about 4 kilohertz. But why measure the envelope when you can actually measure the frequency in real time? If you measure the time, if the frequency is a time series and spectrally decompose it by taking a Fourier transform, you end up with a curve like I've got on the right-hand side there, which is the mean noise, or the mean spectrum of frequency fluctuations of the laser. And because of the equivalence of frequency and length, you can actually equate that to an equivalent strain. And that's the noise floor of the sensor. And so the way to read this graph is to say that at 1 kilohertz, the minimum detectable strain is about 1 part in 10 to the minus 14 or 100 femtostrain. And in fact, if you actually overlay known fundamental noise sources on that measured strain, what we find is that we're actually resolving fundamental thermodynamic fluctuations of the optical fiber cavity. Okay, so a practical fiber laser sensor system is obviously a lot more than just an erbium doped fiber with a Bragg grating written into it. So I've just drawn here a schematic of what a full implementation of a fiber laser sensor array might look like. So on the left-hand side here, you've got your pump electronics and your interferometric interrogation system. On the right-hand side, which is a bit that goes in the water, there really isn't anything other than essentially a string of these optical fiber lasers. And because each laser frequency is determined, sits within the stop band of a Fibre Bragg grating, you can basically engineer the laser frequency essentially by adjusting the Bragg wavelength of the gratings. And so you can implement a fully wavelength division multiplex array of very precise strain sensors. But the thing is, these should not be confused with conventional Bragg grating strain sensors. Remember, each sensor is a light source in its own right, and the only light that's being launched into that telemetry fiber is the pump energy. And so you can imagine that making this technology work in practice requires a number of challenges that need to be overcome. And I'm just going to talk about one. So even though the lasers themselves are single frequency, the resonant structures, which are formed by a Bragg grating, have a finite reflection band. And so what can happen is that the light from one laser can be reflected from the side bands of an adjacent cavity and injected back into the laser cavity. And when weak feedback is coherently injected back into a laser cavity, it changes the wavelength it changes the frequency. And you can see from this formula that I've got written here that the frequency omega appears on both sides of this equation, and that is not good. This is a highly nonlinear effect, and I'm going to play what it sounds like when you actually stretch the fiber between two adjacent sensors when there is weak reflective coupling between them. Okay, so that's obviously not good, and that's only weak reflection. So if the reflection becomes as the reflectivity increases, you can completely destabilize the lasers and get catastrophic failure. So back in 2016, we developed a unique Fibre Bragg grating cavity structure, which enabled us to reduce the out-of-band reflections by about 30 dB compared to a conventional DFB structure, as I've shown that in the diagram up on the top left hand. And that enabled us to demonstrate for the first time a high-performance 16-channel fiber laser sensor array. And I just want to acknowledge the really important contribution of Goran and others from Redfern Optical Components, as it was at the time, to that endeavor. In 2017, we went one better, and we actually demonstrated a 32 element array on a single optical fiber, basically by making some minor modifications to our laser design to reduce Rayleigh backscatter, which is another source of external reflection, which is not related to the side lobes. And so that's sort of like the state of the art as it stands at the moment. But we actually, in doing so, we kind of pushed things too far. So the photo on the left-hand side is a fiber optic towed sonar array that was built by our industrial partner Thales, and it actually incorporates the 32 element per fiber architecture that we demonstrated a few years ago. And because that's being towed through the water under quite heavy seas, there are enormous stresses on the cable, and that results in very, very large strains along the array. And what we actually found when we actually on this particular day was that the performance of the sensor array was severely impacted by reflection-based effects, that wobbleboard sound that I played just a couple of slides ago. And so this has led us to kind of go back to the drawing board a little bit and just rethink the design of the lasers. And so we're currently in the process of redesigning the lasers, and I'm really looking forward over the next 12 months or so to working again with Goran and LIGO and on a new round of development. And one of the things we're particularly keen to do is to push the residual side lobes of our resonant structures down below the Rayleigh backscatter limit, so that we can ultimately achieve I suppose the full potential of this exquisite sensor technology. Thank you.
Thank you very much, Scott. I just want to remind you guys that there is a Q&A option in the bottom of the screen. And on that note, I got a question for the Scott. Scott, they're asking if the path length fluctuations in the LED-in cable affects the strain noise floor.
Not so much. Only if there's feedback. So again, I talked about feedback between sensors, but you could also have feedback from, for example, if you've got connectors, for example, within the cable, you could have feedback. So we actually have an isolation element right at the beginning of just before the first sensor to eliminate any back reflection from the lead-in cable. So external strain is really only coupled in through feedback. The effect of external strain in terms of the direct modulation of the frequency is is below our noise floor.
Fantastic, thank you so much, Scott. So I don't think we have more direct questions for Scott, so probably we can move to the next. We will have more time at the end of all the talks if you guys want to go back to ask any questions. So the next speaker is actually Professor Josh Bland-Hawthorn from the University of Sydney, and he's going to be talking on the complex OH sky gratings filters for astronomy. Thank you, Josh.
Okay, so if I hit display on this, you see, does it fill the screen?
Yeah.
Very good, thank you. So my talk's on towards complete suppression of the Earth's narrow-line night sky emission spectrum. And as we've already heard, this is Australia's sovereign capability. When I began this problem in about 2003, 2004, progress was very small, very limited in terms of what could be done in terms of suppressing the sky noise spectrum. And I would say that we've completely revolutionized this, and it was all entirely due to Australian technology, sovereign capability, largely then through Mark England, Goran Edvel, Ligbo Lua, and others. It's been a tremendous working relationship, which is now, well, them and others has been going for 16, 17 years, but it required more than just the grating in the end to solve. All right, so I speak on behalf of the University of Sydney, of course, director of the astronomy group. I'm also a project scientist for the Cell Labs. This is something that is directed brilliantly by Sergio. This has some of the technologies now a part of the ANFF facility. And Australis, which is a working group, which is a sort of a consortium of a number of ANU, University of Sydney, Macquarie, building advanced instrumentation for the next generation telescopes. Okay, so you might ask the question, why are we fighting with the Earth's atmosphere, as I have been doing for 30 years of my research career in different ways, when you could build something which goes above the atmosphere and you avoid it altogether? Anything space-based costs you 100 to 1,000 times more, and that's not going to change. Another thing to be aware of is the larger telescopes will always be on Earth. If you want to collect more and more light from fainter and fainter sources and see back to the Big Bang, you need very, very big telescopes, and we're getting into a new generation of very large telescopes. They'll always be on Earth. So that's an important point. So you've always got to look through the Earth's atmosphere. The trouble with the Earth's atmosphere is manifold and manifest. It moves, it changes a lot, which causes twinkling. We use adaptive optics to try to solve that. But you've also got this glowing atmosphere because of the OH molecules in particular that glow at you, and they're causing extremely bright emission lines. Let me just play a movie for you. This is an old movie now, 30 years old. And these waves that you see going by these are emission line regions glowing at you and then basically moving across the sky as gravity waves, glowing at you in these thousands of these very, very intense lines, which are only picometers in width. And these are the lines that we want to knock out with Fibre Bragg grating technology. Now, adaptive optics is the other major problem, and we've spent billions on solving that. The military, of course, have also spent billions on solving this. Astronomy today now has the most advanced AO systems in the world, and the solution has been to shine lasers up to the altitude, the sodium layer of the atmosphere at 90 kilometers and produce fake stars, coherent stars, which when they come back through you, allows you to monitor how the atmosphere is changing, and you correct for that with the complex conjugate of the variation of the signal. Now that's an industry which has been extremely successful and it's used worldwide now, and it's going to be used on all the future telescopes. But no, the same consideration has never been given to suppressing the background sky emission. And without question, we are the world's leaders in this technology. We're sort of far and above, have the most advanced solution to the problem. So here's the problem. So below the atmosphere, this is the optical region, the I band, as astronomers call it. The J band is infrared, H and K. These are all infrared parts of the spectrum. And there are these natural bands that we work with in astronomy. And these are sort of water molecule absorption features due to the atmosphere itself. So we work in these bands. So these are the bands that we want to correct for this emission below. This is what the atmosphere does to you. It glows at you in these extremely bright lines. They're like tens of picometers wide. And then you've got nanometers of spectra, of spectrum between these lines when you zoom into them. If you could knock out all those blue lines, get to that red line, that is sort of the ultimate background caused by the zodiacal dust in the solar system. But right now, the background that we have to deal with in the telescopes is, as you can see, orders of magnitude higher. So what we want to do is somehow knock out these lines and get down to this sort of fabled or fictitious background that we all dream of. And the lines themselves account for about 99% of the background in the J and H bands and the infrared, which are the most commonly used regions of the spectrum to look at high redshift galaxies, like with the Hubble telescope and with the future generation of telescopes. So this is what it might look like. If you shove that spectrum through a spectrograph, working at some moderate resolution, the lines will get broadened out like this, and they basically start connecting up. And that background with respect to the objects you're looking at, as you can see here, is orders of magnitude higher than this background. This is a log scale. And these are the faint objects that we want to be seeing, like little galaxies, like surrogates of the sort of precursors of the Milky Way, going back to 13 billion years in the early universe, looking for the things that built the Milky Way. You're looking at little faint things like this, and this is a spectrum, whereas the sky you're dealing with is way up here. So how do we suppress this sky at high resolution and bring that background down to what's more like compatible with this object? That's the challenge. So the photonic solution, as I identified years ago, looks like this. Suppress the sky before the light enters the spectrograph. If any of the OH spectrum gets into your instrument, it scatters like crazy, and you just can't control it, and it starts to pollute as a general background on your detector. So you have to remove the light with a filter even before it enters your instrument. And that, by definition, means removing these lines at high resolving power, tens of picometer widths, not like conventional astronomy technology, which is like angstroms in widths or even tens of angstroms. And we want to maintain high overall throughput. We don't want to have this, of course, you can knock out the spectrum by putting a brick in front of your telescope. That's not very helpful. So you want to suppress and maintain high overall throughput. And so our requirements that we identified very early on is high performance broadband Fibre Bragg gratings. And those didn't exist when we started, aperiodic gratings. And Australia really was the place to. I traveled the world looking for solutions, but the solutions were right here in Sydney. And then another technology, which was developed by Sergio, myself, and Tim Burks at Bath, were these things that we call photonic lanterns. We wanted to convert multi-mode light in astronomy fibers into single mode outputs and insert gratings into the single mode fibers. And the other thing we wanted, of course, was a high performance infrared detector. At the beginning of this work, they weren't very good. Today, infrared detectors are much, much better, which really helped us start to see information at very faint levels. So, of course, all technologies, there's an evolution involved. There are loads of papers on this technology we've written over the years. We've been very good at publishing. We must have 20 or 30 papers now. I suppose the one paper that captures all of the story, the narrative, if you will, is this one in Nature in 2011. Myself, Simon, you'll hear about him in a moment, Scott, Sergio, and others. This paper tries to sum up what we have discovered in developing all these different research papers. I should also say that it's been a long journey and struggle. We've gone through technology changes, evolution, we've gone through funding changes, we've got money coming in from all over the place. We've built prototype instruments, we've built major instruments, and this is like an ongoing story. And we see the new ANFF facility as part of that ongoing story, but it all began with conversations with Mark England in February, Valentine's Day, in fact. That was a very romantic day for me, at least. The start of all this in Valentine's Day 2004, talking to Mark England over at the technology park. All right. So the technology looks like this. You have a photonic lantern which converts multi-mode light into single-mode light. This was a major step. We were told early on that this was not possible, and Tim Burks and Sergio's brilliant thesis at Bath, through a lot of mucking around and very interesting conversations, we were able to come up with this beautiful technology, converting multi-mode to single-mode light. And this single-mode light, we put a series of identical gratings in these, and then the single-mode output signal, you go through, reverse the process of this lantern by going back into a multi-mode fiber. And the point to be aware of is the number of fibers or the number of single-mode fibers and number of gratings you need is basically the number of spatial modes, unpolarized spatial modes on input and on output. And that's a problem that we solve. We'd like to bring all this into multi-core technology, and we haven't yet achieved that, but we're hopeful that this will be possible in the near future. It looks something like this, a multi-mode fiber undergoing some kind of a taper, a bunch of single mode outputs. These single mode outputs can be put back into a lantern and gone back into multi-mode. It's a reversible technology. All right. So this is what we achieved. Take this part of the spectrum. This is part of the spectrum which is of great interest to astronomers, the sort of the bluish part of the H band. And you blow this up and you find that there are loads and loads of these lines. These lines are extremely bright OH lines compared to the background source that we're looking for. This line here, for example, is 10,000 times more flux in a 10 picometer beam. No, sorry, in a 1 nanometer beam than there is in the next nanometer beam of the source itself. So you're looking to get rid of all these lines. So the idea was to develop gratings that were very square in shape, very, very narrow, and matched the amount of information in these lines and spacings. So the grating that we achieved is shown here. This is that was done in 2 parts, blue and red. This incredible aperiodic variable grating. And notice that because of Parsifal's theorem, when you design these things, the way in which the strength of these lines is varying in concert with the lines themselves. There's no point having sort of 40 dB of suppression on a faint feature and having 40 dB on the bright. You might as well have all the strong suppression in the bright features and use the faint suppression in the fainter features because that gives you essentially more information, kappa information to put into the grating design. So one of the things we realized was the interline continuum is not perfect. You know, we don't have 0 loss. We have sort of order 0.2 dB loss, which is fantastic compared to the notches being around 25 to 30 dBs. However, we could probably improve on that in the future by removing cladding modes from the multi-mode and single mode fibers. So that's something we haven't yet solved. But in any event, this did not really affect the overall losses of the system. But we would like to get that to 0 loss interline. I should also mention the notches are very square. They're like sort of Butterworth profiles. They're not sort of Gaussian functions or triangular functions, which if you just miss, you have a great deprecation of the suppression. It's nothing like that. These are individually, each of these notches individually has been made square. And that was a beautiful insight by my Russian theory colleagues, Sasha Buryak and Kazimir Kolosovsky. They were the ones that realized how to make these square and conserve the total amount of information in the grating. It's an amazing achievement. So if you go off and look at what the sky looks like, you've got this very, very bright background spectrum here. This is what we're fighting against. And our technology removes most of those bright lines. We get it down to this. You can see now that the sky has been largely removed. This signal here is like a suppressed sky spectrum, which is a signal we still don't want. So we're able to subtract that off using conventional analytic techniques, get down to this spectrum at the bottom. And if I have to zoom into that, like this spectrum in here, you see these faint features. That's an absorption feature in a star from the CO band, and an ion 2 feature from gas around the star. And this is the signal that we're looking for, this feature here and this feature here. You can see how impossible it would be to find those features in a distant galaxy when you're staring at that lot, the forest of bright lines. So this is the technology we want to get onto the big telescopes, because we think we'll see the furthest galaxies ever observed with this technology in Chile in 2 years' time. So just to say that I know I don't have much time left, I'll be very quick. This instrument has been tested on the Warren Bungles telescope, Siding Springs telescope in the Warren Bungles National Park up at Coonabarabran. It's a beautiful location if you haven't been there. This is an amazing world famous telescope. And I want to pay due credit to Simon Ellis, who has carried this project forward. He's a tremendous individual who's worked on every aspect of this with us and on building these instruments that allow us to incorporate technology. That same instrument is being rebadged and repackaged to go down to Chile in 2023. We call that Eupraxia, European Praxis, basically, the Very Large Telescope. And the idea of, and the Europeans, the ESO crowd, we're part of the VLT. We're the only non-sort of European nation that's basically a part of that, except for Chile, because of the land rights issue of where the observatory is. But they've allowed us to do this on the VLT by 2023 to demonstrate how powerful this is on very distant galaxies because of their interest and our interest in getting this technology onto the ELT. This is a 40-meter telescope that is being built right now. They're like a third of the way through the project. They'll deliver this by 2027. And I guarantee you, if we get our technology working on this, and they allow us to get onto this, we'll have the most powerful technology, spectroscopic technology in the world for seeing the most distant galaxies. So we're very excited about that. So my final slide. So this era of complex photonic solutions to astronomical problems, this general field is called astrophotonics. There's a special issue that came out a few weeks ago in JOSA B and Applied Optics, 28 papers. So you can read much more broadly on how photonics is being applied to astronomical problems. But the FBG problem in particular, I think is going to be with us for years to come. Thank you.
Thank you very much, Josh. Wonderful talk as always. I think that we probably want to wait for the end of the seminar for opening the Q&A. So we give a chance to John to go ahead now. But I just want to mention, Josh, that your lovely Russian colleague Casimir is in the audience. I can see. So
Casimir's in the audience.
I think so. But anyway, we can talk that offline. I'm
glad I cited him.
Okay, so well thank you very much, John. Please, John Bartholomew is working in quantum optics at the University of Sydney, part of ACUS, and is going to be talking about optical narrow filters for quantum optics. So thank you very much, John.
Thanks very much, Sergio, and thanks very much everyone for coming along today, and indeed for the ANFF for hosting this webinar. So in contrast to both Scott and Joss, I guess I'm a newcomer to a collaboration with the technical expertise that exists within the FBG facility, and so I guess I wanted to give you a perspective as a new user, but also as a new use case in terms of using this really highly specific technology for developing quantum technologies, and that's my area of interest. I investigate the use of optically addressable spins in solids to be able to create connections between different types of quantum technologies. And so I'll give you a bit of an overview of the things that I'm interested in today, and a particular use case, as well as pointing to some future uses that I envisage for this type of technology. And so, I mean, the starting point for all of this is that the quantum mechanical regime offers us a completely different way of doing a lot of things, because we can overcome the limitations imposed by classical physics. And so there's a lot of attention at the moment for using quantum mechanical systems for computation, for measurement, and also for pushing into new regimes of science by overcoming these limits to achieve precision measurement. It's also considered for different types of applications, including both creating new encryption protocols as well as breaking current encryption protocols. But the power in all of these applications exists when you create connections between quantum systems. And so, you know, having two quantum systems as an elementary link, you want something that's going to link these systems up efficiently, to have a very high fidelity transfer between the two systems, and ideally you want this connection to be scalable with distance, or indeed the complexity of your network. And so the things that you need to be able to develop this type of system are stationary qubits, and so these are quantum systems that preserve the local quantum state during an operation, and you also need networks of these to be able to allow you to do processing. To create a network, you also need flying qubits, so something to distribute that quantum information between the different systems. And you want these links to be low loss and low noise. And so it's really in this flying qubit aspect that I've had the most experience in terms of using light as a very low loss and low noise carrier of quantum information. To develop these complex and more robust quantum networks, you then need to start linking up stationary qubits with flying qubits. And as I'll show on the next slide, this is not always straightforward. And so as you build towards more and more complex quantum systems, it's not just the quantum systems themselves that you require. You actually need to start building a number of devices to enable you to build up these robust and complex systems to allow you to harness this quantum mechanical technology that we have. And so these include things like sources of quantum states, memories to be able to store quantum states as well as synchronize different parts of your network. You need processing to correct for errors and the inevitable non-idealities that occur within networks. And the aspect I'm going to focus on today is that you also need converters or transducers. In the same way that you need them for classical networks, not everything in quantum systems work at the same frequency or at the same operating regime. And so you need devices to be able to work or shift information between different regimes. And a really good example of that is a challenge that's one that's really I guess being tackled in a lot of ways around the world at the moment, which is how do we connect some of the most powerful quantum computers that exist at the moment? And so one of the leading technologies for quantum computing is based on superconducting circuits. So these are microwave frequency domain devices that operate on on superconducting circuits that must be held at extremely low temperatures, so around 10 millikelvin, to avoid sending the superconductors normal, but also to keep the noise low in these systems. And so at the moment, one of the limitations on these systems is how many qubits or elementary components of a quantum computer can you actually cool down in the one fridge. And this is a challenge because you have to address each of these particular qubits. You need a lot of wiring to do that. And so the size of the fridge or the cooling system that you need is actually one of the big challenges. What would be one solution to this problem is to be able to link up smaller fridges to modularize the system. And so there are examples in research labs around the world where people are linking up these extreme low temperature systems over tens of meters through ultra cold links. But this isn't the ultimate scalable solution. And so what ideally we'd like to be able to do is to take a microwave signal from one of these superconducting circuits to transduce or transduce that signal into an optical photon, and then send that photon down an optical fiber link, and then reverse the process at the other end to make that quantum connection with another processor. And so what this allows us to do is to utilize different technologies for exactly what they're suited for, in terms of the superconducting cold processing, which is shown to be one of the more powerful technologies at the moment, along with optical fiber technologies, which has been the state of the art for sharing quantum information over long distances. And so while this is one particular use case that we're interested in, there are, of course, a generalization to that, which is that if you have other quantum technologies, so these might be other spin qubits in solids, they might be atoms in traps, they might be atoms held in optical lattices, whatever the quantum system that you're interested in for a particular application, it'd be nice to be able to start connecting these up using light. And so to do that, there are two devices which you can think about. One is conversion between different optical wavelengths using non-linearities in optical materials. And the second one is the quantum transducer, which is something that's shifting regimes. So here I'm thinking about shifting between a 5 gigahertz signal to a signal that is at around 1550 nanometers. And so the transduction, this problem of taking a microwave photon and turning it into an optical photon, is one that boils down to basically creating a coupling between two different types of cavities, one cavity operating in the optical regime and one operating in the microwave regime. And so to do that, you want to introduce some coupling between these two types of cavities. And so if you tune that coupling strength between these two cavities to a particular condition, depending on the relative loss in the optical and microwave cavities, you can achieve this effective impedance matching condition where your transfer efficiency between those cavities approaches unity. And so if people are more interested in this field in general, there's a couple of nice review papers that came out last year. But in terms of the technology that's out there at the moment, one of the leading platforms in terms of efficiency is an electro-optomechanical system, which couples basically a mechanical object to a microwave circuit, and that mechanical object then modulates the frequency of an optical cavity. And so these devices have achieved around 50% efficiency. The one that I think many people will be most familiar with is an electro-optic scheme. And so these are the basis of the technologies, for the EOMs that are quite commonly used in research and telecommunications. But those devices have extremely low efficiency, whereas in the quantum domain, what we really want to do is to push that efficiency up, as high as we possibly can. And so the base of that technology, which is a Chi2 medium, which is sitting in the capacitive part of a microwave resonator, is then used to create this coupling between the microwave resonator and an optical resonator. And so these are some of the systems that have achieved quite good efficiencies and the largest bandwidths at this stage. A second to final example, which was recent work that came out last year, extends this type of idea by using multiple degrees of freedom. So here, a microwave photon is transduced to an optical photon by harnessing a mechanical degree of freedom as well. And so in this experiment, what researchers from Oscar Painter's group at Caltech were able to do is to take a single photon generated by a superconducting qubit and transduce that into a single optical photon, and then measure the quantum state of that superconducting qubit based on the measurement of the optical photon. My own work is with rare earth ions in solids. And so this scheme uses, rather than an electro-optic effect or a mechanical or another effect, it uses optomagneto or magneto-optic effects. And so this is where we have a medium of rare earth ion spins, which have both microwave and optical transitions. And we couple the spins both to the magnetic part of a microwave cavity and the mode of an optical cavity. And so this is an idea that was first proposed and really pushed forward by Jevon Longdell's team at the University of Otago. Along with my colleagues, when I was at Caltech prior to coming to the University of Sydney, we were able to miniaturize this device to an on-chip, prototype, where we were able to show coherent transduction between the microwave and optical regime with very low efficiency on chip using these types of materials. So that's an overview of some of the technology that exists within this space, but they all have a common challenge. And that is that if you want to transduce, in this example, a single microwave photon to a single optical photon, that's a huge energy gap that you need to mediate. It's about 4 orders of magnitude. And so you need to get that energy from somewhere. And typically where that energy comes is from a strong optical pump that's driving the system. In our case, it's driving a particular atomic transition to help us mediate that transduction. But in other systems, you're driving a resonance, off resonance to achieve this transfer. And so here, the challenge is that you're going to have a single optical photon that you care about, along with a large background due to the residual pump beam that propagates through the device. And so what you'd like, and I guess what I approached the FBG team with, is that you'd like a filter that gives you around 12 orders of magnitude suppression from a very low insertion loss beginning over the space of about 40 picometers or 5 gigahertz. And so this is an extreme type of filter in the optical regime. And so just looking at how people commonly solve that challenge is by concatenating basically cavities, fiber-based cavities. And so one common solution is to use these cavities, for example, from stable laser systems, which give you a suppression, a very low insertion loss at your target wavelength, so less than 1.5 dB, and give you a suppression of around 60 dB 5 gigahertz away. And so by concatenating 2 of these, for example, you can achieve the type of performance that you want. And so the challenge I put to the team was, can we do better than this, or can we approach this kind of performance with a Fibre Bragg solution? And so I guess we're in a preliminary mode at the moment, largely affected by the lockdowns at this stage. But there's been very promising results in the initial prototypes. And so this is one example. So here we have the target wavelength of around 1536 nanometers. And we have a very low loss, around 1 dB insertion loss. And then we have two blocking bands that come down either side of this transmission band. And so you can see two curves on this trace. One is a measurement, and that's done by a tunable source and detector with a dynamic range of between 55 and 60 dB, along with the theoretical response based on the Fibre Bragg grating design. And so you can see here that the design, the performance of the device matches the design quite well until we get into the dynamic range limit. And so we're very excited to push forward with this kind of notch filter to see how far it actually pushes towards the ideal response. And so once we're out of the lockdown situation, we'll do those higher dynamic range measurements to see how far this device pushes towards that theoretical ideal result. Other aspects which are really appealing about this type of technology for quantum applications are that they're shown to be quite stable. You can tune them and you can also switch them quickly. And so all of these allow someone like myself who deal with atomic systems to start thinking about, I can dynamically switch between different optical transitions, but also have a nice stable reference for the system that I'm using. However, I guess, again, once we get through the lockdown that we're in Sydney, we hope to start characterizing all of these in detail. So very quickly, just before finishing, I wanted to point towards things that I'm really interested in for these filters in terms of being able to simplify what can be very complex atomic spectra. And so this is a diagram of the spectrum of two levels of an erbium-167 ion in the solid state, where the brightness of the line kind of indicates the strength of that transition. And so this is a subset of 256 transitions, which then is a subset of many, many more transitions that occur in this element. And so what we tend to do in my field is to try and harness this energy level structure for things like quantum memories, sources of photonic entanglement, to utilize these systems as spin qubits and transducers, as I've mentioned. And so having both the extremely high spectral resolution that you can achieve with these Fibre Bragg gratings, along with a low loss platform coupled directly to fiber, and also compatible with both room temperature and cryogenic conditions, it gives me a lot of optimism for what we might be able to do in the future using this type of technology. And so with that, I'll leave it there, and happy to answer any questions in terms of the application, but we'll leave it to the experts in terms of the Fibre Bragg gratings if people have specific questions there. So thanks very much.
Thank you very much, John. Fantastic talk, like all the ones today. That is, I'm checking the questions, and let me just share the screen so we keep it here on the. Okay, let me see. Do we have any questions for you here? Yeah, I got one from Kalaga. He's actually Kalaga is one of our colleagues in astrophotonics, and he's now in Germany. So thank you very much for waking up so early. Kalaga is asking if you are using the pi-phase shift grating to achieve the narrow band. And
yeah, so I think, yeah, I mean, Sergio, you might like to speak more to it, but I mean, I guess this is part of the design in terms of, I guess, extending from a simple pi shift grating to I guess, higher phase shifts grating. And so, I mean, Sergio, you might like to speak more about that.
Yes, I mean, in fact, the team came out with a very interesting design, which also makes this capability unique to implement that. We actually went to have 5 and 7 pi phase shifted periods on each of the gratings. So like that, would you actually increase the transmission bandwidth when reducing the separation between the side lobes of the pi-phase structure? So this one that John showed in particular is a 7th pi phase shifted grating. I think I've got another question from George Broley. What loss may be tolerable in the optical passband for using quantum interconnects? Can the grating achieve this?
Yeah, so it's a good question. I mean, the ideal, of course, is like the lower loss you have, the higher fidelity your operations are going to be able to be, and the longer or the more complex networks you can build. So I think the other way to look at that question is that whatever your loss level is, that will limit your networks. But certainly the fundamental is that you need to be above 50%. But ideally we'd like to push that efficiency up as high as we can. And I think we're just scratching the surface of what we can engineer with this grating technology. So obviously, it's not just the grating itself which limits that efficiency. It's also in coupling, out coupling, and all of these other aspects which occur on these on-chip devices. But I'm optimistic that these Fibre Bragg gratings are going to be very, very useful in the quantum optics space.
Could I make a comment, Sergio, if there's no active questions?
Of course. We're in the Q&A question, so we can actually.
So I was just really interested to look at that that grating structure that you showed, that transmission structure that you showed, John. So we can actually measure down to about 100 dB with for our devices, and so we've actually had devices that we've had made by Goran and LIGO, where the transmission extinction is well below we can see that we hit the noise floor at minus 100 dB, so it's well below 100 dB. So I'd be fairly confident that they can probably achieve the type of performance that you're looking for, or close to it.
How do you do that?
How do we do it?
Yeah.
So we basically use a tunable laser, and then we use an OSA as a detector, and so we have so the instrumentation is synchronized. So it's quite an involved measurement. To be honest, off the top of my head, I couldn't give you the details. It's been a while since I've given it any thought. So because it's all basically, we have a sort of a LabVIEW virtual instrument which controls a tunable laser and an OSA, and somehow magically we're able to extract 100 dB of dynamic range.
I mean, that's been one of the limitations with improving the design for John in the facility, is to be able to get the high dynamic range measurements right. But it's looking promising, and we're improving the system within the facility to be able to measure that too. So I got another question actually from Jake Rochman. He's asking what is the highest finesse that you are able to achieve with these Fibre grating cavities. So probably Scott got an idea there too.
So yeah, so we're pretty confident that we can see. So I mentioned sort of a number of 8 by 10 to the 8, and that's not the strongest cavity that we've seen. So the question that's a little bit uncertain is what's the loss? Because obviously the finesse is not just the strength of the mirrors, it's also the UV induced loss comes into play. And we don't have a good handle on that, but what we can say from there are ways from the dynamical behavior of our lasers that we can infer the cavity Q. So what we see a unique phenomenon that's never been observed before, and that is that the relaxation oscillation of the laser is completely eliminated, and you can sort of calculate the cavity Q that's required for that to happen, and it's of the order of 10 to the 8, 10 to the 9.
Impressive. I got actually a comment more than a question from an anonymous attendee. Is to Scott, saying that the polarization in the OSA and other bits and pieces are really important during the measurements, so that may limit some or masquerade some of the high dynamic range.
So we can see, we'll generally see 2 gratings superimposed. So we'll see the 2 polarization modes on. In terms of the interaction with the actual instrument itself, I'd probably have to ask one of my one of my experimentalists. So I'm sort of more of a theorist. So that level of detail is probably beyond me.
So I don't have any current questions at the moment there, but if you guys are happy to mention anything else, so what you would like to, one thing I want to comment quickly is actually that the facility is actually already up and running. So we'd like you to encourage you, if you have any application for use for it, to contact the facility. We will provide them probably a flyer with some contacts after this to the attendees. And also you can contact the organizer, Tont or myself, as initial contact, and then we can go from there. So, anything else? Sorry, Scott, I think you were about to make a comment about something else.
Oh, no. I was just going to say thanks for inviting me.
No, that's good. That's exciting. And I also, there are things that are coming, which is quite encouraging with the work with John. We're getting interest from other colleagues putting very crazy ideas forward. And that's another thing. I think that we are here for the challenge. I think that to have crazy ideas is a good thing. And I'm hoping to see many of those coming from this group here on the attendees. So,
I think it's worth stressing, Sergio, that it was always the case with the ROC group beforehand, Subcom, but it became less so as Subcom went to big contract approach, big industry. We're back to the R&D days where we really can explore almost any ideas that people have. It used to be like that back in 2000, 2005, that time frame, or maybe a bit later, and we're back to those days because the university setting for ANFF really encourages that, and I think we have many more ideas we'll ever get to. And some of these ideas can be morphed into other ideas. So if people come along with even a sort of a sense of what they want to do, and we can maybe morph it or shape it into something more appropriate. So we're back to those R&D days.
Yeah, no, that's a extremely good point, actually. And that's one of the reasons that during the period in which T Connectivity and Subcont bought ROC, ROC was used as a factory for a standard grating for the submarine cables and installations. So that R&D component with this facility was actually a little bit lost. So I think it's extremely important that ANFF have helped to bring this back to the Australian community.
Yeah, I just want to echo that. I think I'm really excited about the fact that, it's probably been 10 years since we've had this kind of access to the facility and the opportunity to work genuinely, collaboratively.
Yeah, that's extremely exciting. So, Jane, anything else that you want to say to close the event?
I just thought I'd jump in there and say thank you for the presenters for giving us such an incredibly interesting seminar on the kinds of applications that using a laser into a small little bit of fiber can actually achieve. Like when we think about what we're actually doing and what it can achieve, it's actually my scientific nerding is going off the charts today, so I'm very happy. So thank you to all of the speakers, and I'll just echo what Sergio and the rest of the speakers have said. We are incredibly proud to have brought this facility back into the research and development community for Australia. It's open, it's there. We have the experts there who are driving this facility forward. So if you do have those crazy ideas, it will be a wonderful place to come and explore those ideas. And if we need to find collaborators, we've got the collaborators who are already working in these facilities that can help. So really bring your ideas, come and talk to us, and let's see how much more we can get out of this facility in the next little while.
Fantastic. Thank you so much, Jane. That was the perfect height to finish this. So I think that we don't have any more questions. And
good question here about who do they talk to? Who's the point of contact? That's an important question.
So point of contact, you've got Sergio, who you can talk to directly. We've got the ANFF national website, so that's anff.org.au. So jump on there, contact anybody you feel like contacting, and we will point you in the right directions. So please, anff.org.au is a pretty good place to start.
Fantastic. Thank you so much. So again, thank you everybody to be here, and thank you especially to those guys abroad that have been following us. I know at least 2 or 3 there on that list. And that has been a fantastic event and launch, and very excited to get this going. So thank you all, and thank you for your time. Have a good day.
Thanks. Thank you, everyone.